Let's explore a really cool idea. What if you could build a perfect virtual copy of a really complex machine, or hey, even an entire factory, and then just let an AI loose inside of it? Think of it like a digital sandbox, a place where an AI can run millions of experiments, learning to master the real world, but without any of the real-world cost or risk. This whole concept is called a digital twin, and we're going to see how it's so much more than a mirror of reality. It's really a training ground for intelligence.
But first, let's start with a puzzle. Picture this. There's a machine on a factory floor, say a plastic injection molding machine. It's been running like a dream for weeks. The settings are dialed in perfectly. Then, one morning, it just starts spitting out thousands of bad parts. Nothing's changed, no alarms went off, the settings are exactly the same. So, what happened? Just hold that question in your mind. We're going to come back to it. So to figure that out, here's our roadmap. First, we'll talk about the ghost in the machine, that hidden complexity that makes modern manufacturing so tough. Then we're going to build a digital twin from the ground up, layer by layer, and see how it becomes this sandbox for reality. After that, we'll look at some real-world examples, the big challenges still out there, and then we'll wrap it all up with 3 powerful mental models you can take with you. All right, first up, the factory's ghost. Let's really dig into the core problem here. I mean, why are these processes so hard to control? It feels like we should just be able to set the dials and walk away, right? Well, the thing is, a process like making a plastic part is this incredibly delicate dance. You've got dozens of variables all interacting. There's the mold temperature, the fill time, the injection pressure, the exact chemical consistency of the raw plastic pellets, even the humidity in the air that day. A tiny, tiny drift in just one of those can set off this cascade of effects that ruins the final product. It's kind of like trying to find your way through a landscape covered in a super thick fog. You can only see a couple of feet ahead, and you have no idea how the whole train fits together. And this isn't just a metaphor, it's a well-documented problem. I love how this 2024 paper from the journal Systems puts it. The sheer number of parameters makes it pretty much impossible for a human, even a super experienced one, to really perceive and master the whole system at once. That's the ghost in the machine we're trying to hunt down. So the big question is, how do you cut through that fog? And that brings us to the digital twin. But, instead of just throwing a dry definition at you, let's build the intuition for it. Let's actually build one together, from the ground up. Okay, so step 1, you start with a blueprint, a simple CAD drawing, a 3D model. It's static, it doesn't do anything. Now, for step 2, we add physics and time. Suddenly, it's a simulator. It can show us how the machine should work in a perfect world. Okay, now step 3 is a huge leap. We wire up the real machine with a bunch of sensors and connect them to our model. Now it's not just simulating, it's a digital shadow reflecting exactly what the real machine is doing right now. But the final step, step 4, this is the magic. We make it a two-way street. A true digital twin has a full duplex connection. That means the virtual twin can send commands back to control the physical machine. And this brings us to a super common point of confusion. We have to pause here because people use simulation and digital twin like they're the same thing. But they're not. They are fundamentally different. A simulation predicts how a system should behave. It's a what-if tool for an ideal world. A digital twin, because it's hooked up to live data, mirrors how the system is actually behaving. It's a what-is tool for the messy, real world, with all the wear and tear, all the little variations, all the stuff that causes that mysterious factory problem we started with. Okay, so we've got this perfect real-time mirror of reality. For just monitoring things, that's amazing. But how do we turn it from a passive dashboard into an active, intelligent problem solver? Well, this is where the AI comes in. And this is the real click, the big payoff. Here's the core insight. This high-fidelity twin creates the ultimate sandbox. An AI can now operate this virtual machine. It can try 1 million different combinations of settings, 1 billion even, just to see what happens. It learns from every single virtual success and every virtual failure. And this all happens in microseconds, with zero physical waste and absolutely zero risk to the real-world equipment. It's a completely risk-free playground for mastering a complex task.
So when we say an AI, what are we actually talking about? If you look under the hood of the system from this case study, it's not some single monolithic model. It's actually this really elegant 2-part system where each part has a very specific job to do. Part 1 acts as the physics engine for our sandbox. It's a supervised learning model, in this case something called an extra trees regressor. Now all you need to know is that tree-based models are awesome at learning really complex nonlinear relationships from data, which is perfect for this. It's been trained on mountains of historical data from the real machine, so its one job is to answer a simple question. If I use these settings, what will the quality of the final product be? It becomes a super fast, super accurate stand-in for the real machine. Then you have part 2, the operator. This is a reinforcement learning agent. And here's the cool thing. It starts off knowing absolutely nothing about how to run the machine. Its job is to learn by trial and error. It plays inside the sandbox that the first model created. It tries a bunch of settings, and the physics engine gives it a quality score, a reward. The RL agent has a very simple goal: get the highest score possible. And the way these two dance together is just beautiful. The RL agent takes an action, it proposes a new set of machine settings. The supervised model instantly predicts the quality, which acts as the reward. The RL agent learns from that outcome and tweaks its strategy. Then it does it again, and again, and again, millions and millions of times. It rapidly explores this vast space of possibilities until it finds the best way to make a perfect part, even if the real-world conditions are slowly drifting. This is how we solve the mystery of the factory machine. So look, this isn't just a clever idea on a slide. This exact two-part AI architecture was put to the test on that real-world plastic injection molding problem. So, let's stop talking theory and look at the actual results. How did it do? To make this super concrete, these are some of the actual dials the AI got to control. Things like mold temperature, the fill time, cycle time, peak pressure. The AI had control over 12 different variables like these. Now, imagine trying to tune all 12 of those perfectly, by hand, in real time. It's just not something a person can do. So first, they had to build a really good sandbox. The researchers tested a bunch of different models to act as that physics engine. And you can see here, the extra trees regressor was the clear winner. It had the lowest error and the highest R squared, meaning it did the best job of predicting the real-world quality. Why? Well, it's great at handling the kind of noisy, complex data you get from a factory floor. And it makes sense, right? The more accurate your sandbox is, the better your AI agent is going to be when it trains. Okay, sandbox built. Time to train the operator. They tried a couple of different reinforcement learning algorithms, and it turns out that PPO, that's proximal policy optimization, learned the best strategy way more efficiently. PPO is often a great choice for these kinds of problems because it tends to make safer, more stable updates. And that's exactly what you want when you're controlling a very expensive, very real piece of equipment. You don't want the AI making wild, random guesses. It just goes to show how much algorithm selection matters in the real world. And really, this idea is exploding way beyond just this one factory. In aerospace, Rolls-Royce has digital twins of their jet engines flying right alongside the real ones, predicting failures and optimizing fuel on the fly. In energy, companies like Siemens and GE are twinning massive gas turbines. Car makers use them to test virtual prototypes. It's even being used in urban planning to simulate traffic flow and infrastructure changes in smart cities. This sandbox idea is genuinely transforming how we design and operate the world. Now, as incredible as all this sounds, let's be realistic. This isn't magic. Building and deploying these AI-driven twins at a massive scale, well, it comes with some really serious challenges. These are the problems that the whole field is trying to solve right now. And these challenges are big ones. You've got interoperability. How do you get a twin of an engine, made by one company, to talk to the twin of an airplane wing, made by another? Then there's data scarcity. You might have tons of data for when things are running smoothly, but you probably have very little data on rare, catastrophic failures. How do you train an AI to predict something it's almost never seen? On top of that, these things require massive compute power, and the models have to be constantly updated as the real machine ages and wears down. But maybe the biggest question of all is uncertainty quantification. How do we know how much to trust the twins' predictions, especially when lives are on the line? These are the huge, open questions that are driving all the current research. Okay, that was a lot, so to make sure this all sticks, let's just boil it down to 3 powerful mental models that you can walk away with and use. The first and most important one, just think of a digital twin as a sandbox for reality. That's it. It's a safe virtual copy where you can experiment and let an AI learn at lightning speed with absolutely no real-world consequences. If you remember one thing, remember that. Second, visualize the flow. It's a constant loop. Data flows from the physical world into the cyber world of the twin. The AI in the cyber world makes a decision, and that decision flows back out to control the physical world. This physical to cyber to physical loop is what makes a digital twin truly active and alive. And third, remember the 2-part AI brain. It's this beautiful fusion. You have supervised learning, which learns the rules of the game, the physics of that specific system. And you have reinforcement learning, which then plays the game to find the winning strategy.
One part learns the map, and the other part finds the best path through it. So, let's end with a final thought. We've seen how we can twin a single machine. But what happens when we start connecting these twins together? To twin an entire factory, then an entire supply chain? What about an entire economy? As these autonomous systems of systems start interacting with each other, they're going to create new, complex behaviors that no single human ever designed or could predict. And that leaves us with a really profound question. How do we build systems that we can fundamentally trust, even when we can't fully understand their every move?